everyone. In Calculus 3 we learned that if I have a double integral and I can write f of x and g of y as a product and the region in the xy plane is bounded by constants, meaning it's a rectangular region, then not only is it easy to switch the order of integration, but I can physically pull apart the integral into two single integrals. Again, this is a very special case. Using this, we want to evaluate the following. The integral from 0 to infinity of e to the negative x squared dx. Now if you look at that, it's an improper integral, and in fact e to the negative x squared has no antiderivative. But we need this result very badly, and so the way we're going to do this is I'm going to say let's call this equal to I for integral. Then it would also be true that if I said 0 to infinity e to the negative y squared dy, that would also equal I. So if I multiply these two together, I squared, I would have 0 to infinity of e to the negative x squared, 0 to infinity e to the negative y squared, dy dx in the same integral. Now if I put them together, this gives us this quantity right here. So I went from an impossible problem to now a three-dimensional impossible problem, or so it would seem. But we recognize this right here as something we would use polar coordinates on, namely that x squared plus y squared is r squared, and that if I switch over to polar, dA becomes r dr d theta. So if I do that, then I'm going to have the double integral. We'll figure out what the region is in a moment, but my integrand would become e to the negative r squared r dr d theta. And that we recognize as something we can integrate. Now, right now, this represents the entire first quadrant on the xy plane, since x is going from 0 to infinity and y is going from 0 to infinity as well. If we translate that into polar, that would still represent 1/4 of the xy plane, and r is still infinite, so r would go from 0 to infinity, but theta, since we're in the first quadrant, would only range from 0 to pi over 2. So this gives us an improper integral with just the one infinity. So we'll now write the limit as c goes to infinity, 0 to pi over 2, 0 to c, e to the negative r squared, r dr d theta. So I look at my substitution. If my u is negative r squared, then all I need is a negative 2r, and I'll put a negative 1/2 on the outside. This will allow us to integrate this fairly simply, in fact, and this now would give us the limit as c goes to infinity of negative 1/2, 0 to pi over 2. This was of the form e to the u du, so the antiderivative would simply be the e to the u from 0 to c integrated with respect to theta. Now when I evaluate this, okay, same as before, I have negative 1/2, 0 to pi over 2. But now my integrand will be e to the negative c squared minus e to the c. Excuse me, e to the 0, which is just 1. Now as c grows without bound, this quantity right here is going to approach 0. And that will leave us simply with negative 1/2, the integral from 0 to pi over 2 of negative 1 d theta, which we realize is simply pi over 4. Now remember, this represented I squared, therefore our original integral, which we called I, will be the square root of pi over 2. This becomes a hugely important result in the gamma function that I've posted online. So look at the notes online and compare to this video and we'll complete the picture.